Okay, so we are going to look at the concept of a free body diagram. And this is one of the most important concepts that we need to understand and to utilize accurately and often in our analysis of forces, and then ultimately our analysis of forces in motion, which we're going to get to. A free body diagram is simply a representation of all of the forces acting on an object. It has two parts that I like to see, one sort of traditional part, and then the additional interaction part. So what I want us to be thinking about when we think about a full free body diagram is identifying the forces acting on the object and then putting them in a representation that shows both how strong those forces are and how they are acting on the object. So identifying the interactions, identifying the forces and those interactions, and then representing those forces appropriately on our object. So, two parts. We want to make sure we understand those interactions, and we've talked about that. I think I mentioned it as a force tree, but really showing those interactions. And then two, oops. Well, let's make that a little legible, shall we? An accurate representation, I'll just say forces on object. Now, how do we identify those forces? Remember, we want to look at the interactions. So, whenever we identify a force that's acting on an object, we're going to call this our force tree. We're going to have that force, whatever that force may be, and it is between the object of interest and whatever the other acting object is. Remember, a force is always between two objects. As we develop those interactions, we might look and make a prediction about what the direction of that force is. So, for example, let's say an apple is falling through the air. So there's my apple and it's falling. Why does the apple fall? Well, because of gravity. So if I were going to represent the force acting on that apple, it would be our force of gravity. It would be between the object of interest, my apple, and the other object interacting with that apple, causing that force, which in this case is the earth. And I would encourage you to make a sort of an idea of what direction is that happening and represent that as an arrow on your force tree, on your interaction. So these are our interactions, identifying the forces. Now, how do we take that and transfer it into the true free body diagram? These forces, once we've identified all of them, every force that we have in our interaction list is represented on the free body diagram. Now, the free body diagram is great because you don't have to have any artistic skills. You're welcome to, but you don't have to. So if I have an apple, I can represent the object of interest as a dot. So our object of interest, then in a different color, becomes a dot that we then look at all the forces acting on it. We draw those forces so that the tail of the force is connected to that dot. So in this case, the force of gravity is acting on our apple. The tail of that force starts at the object and extends in the direction the force is acting. So our free body diagram, in this case, we have a single force. We'll do an example with multiple forces. We have a single force acting on the object. It's pointing in the downward direction. And then we label that force. And remember when we talked about the force of gravity, I'm going to encourage you to do this. It's always best just to throw that mass times gravity in there to remind us. So our object is represented by a dot. The forces, the tail at the object. And number two, the direction by the arrow is represented by that arrow. And it's going to also help us as we do this is make the length of the arrow related to the magnitude. All right, so let's look at just another example of a pretty easy, straightforward system, and then we'll do multiple examples of drawing free body diagrams in subsequent videos. But using this sort of idea, this process, to look at what does the free body diagram look like. So this was our apple. Problem up there. What would a free body diagram look like for a book sitting on a table? So there's my book resting on the table. All right, so the first thing we need to do is look at the interactions. What forces are acting on this book? And we talked about a whole bunch of different types of forces acting on the book. So we said that there's the force of gravity acting on the book, and that's going to be between the book and the earth. Good. Force of gravity always acts in the earth vertical direction, so I'm going to represent my downward arrow there. Now, whether you do all the interactions first and then develop the free body diagram is up to you. But if we were going to develop the free body diagram as we looked at our interactions, my first force would be the force of gravity acting down, and that's mass times gravity, just to get in the habit of always writing that in there to remind us that it's mass times gravity. Okay, is anything else interacting with the book? Remember, we're going back to now our interactions. What else is interacting with the book? Well, the table is. So we have the force of the table. Now this is that contact force, that squished force. We called that the normal force. So the force of the table on the book is our normal force. It's between the book and the table. So our object of interest is always present in our interactions. If we can't find two forces where our object of interest is present and another object is present, and it doesn't exist. Those interactions have to have two objects interacting. Well, what direction does the table exert? Well, as it's compressing those, as the book's compressing those molecules in that normal force, it's going to be pushing in the upward direction. So if I were to represent that on my free body diagram, there's my normal force pointing in the upward direction. Now, we know the book is at rest. We talked about the idea of if things are at rest, we're in equilibrium. Those two forces might balance out. So my arrows, I might predict my arrows to be related to the length, to the magnitude. And if the book is at rest, it's not changing its motion, the net force is equal to 0. My ups and downs are going to cancel out, and my arrows might look the same. Now, I'm going to worry a little less about you when you aren't sure, when you don't know what the magnitude of those forces is. The arrows represented appropriately. I think I'd like you to start, I definitely want you to making those predictions and doing the best you can to represent those magnitudes. All right, so that's our basic free body diagram idea. We identify those interactions. They're represented in arrows where the tail of the arrow is at the object and the head of the arrow points in the direction of the force that's being applied. So there's going to be a few example problems in subsequent videos, so watch those and practice doing the free body diagram. It's going to be a very, very, very important part of our force analysis process. Good job.